This show is sponsored by the Proof is Possible U.S. Tour, offering hands-on training to you and your clients in your hometown. Your work, your clients, your liability. Stop guessing. More at proofispossible.com. Enjoy. Welcome to the Building Performance Podcast from Green Dream Group in Chicago. I'm Corbett Lunsford. Today we're talking about high-performance building and retrofits with Iain Walker, who is a building scientist with Lawrence Berkeley National Laboratory. If you have read anything or run any tests that have to do with home performance, especially with airflows and commissioning HVAC, Iain Walker probably was the author of an original document that came out. So thank you so much, Iain, for being on the program.
Thanks, Corbett.
So what exactly does your research entail at Lawrence Berkeley?
Well, we have to think about it sort of a soup to nuts thing. We do some very basic fundamental research where we're trying to answer questions nobody has thought about or answered before. And we take it from that, learn a little bit, and you mentioned, we think about how you do diagnostics in homes. We write the test methods, whether that's at various organizations like ASTM and ASHRAE that some people have probably heard of. And we also do what I'm doing here today. I'm at the ResNet conference talking about all this stuff. I'm talking to contractors and people who are working for utility programs and so on, telling them about, the work we do, good ways to do things. So it's all the way from the basic, physics of airflow in buildings and how we might come up with some very, very clever test that uses this physics in a smart way, all the way to talking to contractors on a daily basis.
Mm-hmm. I want to drill down into information, since that's what, first of all, if you ever see Iain Walker, he looks like a rock star. Clearly, he sounds like a rock star. He, in fact, was a bass player in a band. We'll talk about more of that in a second. But, so clearly, you're like a people person. I mean, you're cool. But you're also a researcher, and you write white papers. I was looking at your list of publications, and there's like the white papers that have been published in has anything been published in 2014?
Yeah, probably just a couple of things. But,
okay.
I lose track of these things because there's always so many things in the pipeline. I mean, that's what a researcher does, right? I mean, there's no point in me writing stuff and it sitting on my desk. You have to be writing stuff that people can read,
And that is my question for you.
Okay.
So I am on the older cusp of the generation of people who like to watch a video about something or like see a chart about it rather than read literally a white paper. In my mind is a piece of white paper with black type on it, no graphics or pictures or anything sexy at all. Probably not going to read something like that, and yet I am your audience, as I understand. Is that correct?
Well, you're right, but you raise an interesting question. The audience is kind of broad, right? There's a wide range of ages and experience and so on, and some of the old-fashioned types, they want to have a piece of paper they can hold in their hand, and often the good idea there is if you can get it down to one sheet that you can laminate that someone can stick in the binder in their pickup truck for a contractor, that's a great way to reach those folks. But I think for the younger generation, for want of a better word, that's not what they're about. I mean, they want an app on their smartphone, and that's the way that they're going to do these things. They want to carry everything around in their pocket. They don't want to be lugging big binders around. They've grown up doing things this way. They spend their days looking at a computer screen, not at paper. And I think that's actually a good transition from the point of view of how sciencey can we make this stuff. There's a limit to what you can do on one sheet of paper. Often we convert things down to tables. There's no equations or anything. But if you have an app on your smartphone, you can hide all sorts of complicated calculations behind that very, very simple interface. And I think that is a good thing for building science. It's going to let us do a lot more complicated things and increase the accuracy of what we're doing. We won't have to make so many assumptions and simplifications like when you produce a table. But for the user, it won't get any more complicated.
Mm-hmm. Now, obviously, there are people in the private sector who have done apps, and you mentioned Rick Karg. And if you don't know who that is, go to his website. Just Google Rick Karg. He's got several apps and sites that are excellent. Is creating the communication outlets part of LBNL's charter?
I would say sometimes. There's a group who run a thing called a Home Energy Saver, and that's direct outreach to individuals. The public can go online and you can run a little diagnostic on your home to figure out what its energy use might be and to give suggestions about how to improve it. And in the background, it's secretly running very, very complex calculations. But the the thing you see on the internet is a very simple interface that any homeowner could use. So those are my colleagues. I personally am not involved with that. But I am involved with a lot of other codes and standards, and there's a big awareness there that for these things to be more used and more useful and used correctly, that we need to have apps and so on. And right now, there's private individuals who are making these things happen. But I think more and more you're going to see the standards writing organizations produce these things. I mean, even at the conference we were at today, there's no printout of when the sessions are going to be. There's no hard copy. It's all on my phone. It's all on your phone. We're going paperless for sure.
Mm-hmm. You brought up the energy saving kind of thing, and I actually am interested because one of the things that you are recently famous for is being part of the ASHRAE ventilation standard. Mm-hmm. Ventilation, as anyone who knows about buildings will understand, is not an energy-saving device. Ventilation is for health. It actually costs money to ventilate a house. It makes it less energy efficient. When is the government and the program language going to kind of understand that it's more about control over the built environment and less about necessarily just all energy efficiency? Because I feel like that's people like me who are out in the field are having to constantly fight against that kind of marketing.
I think you're probably right, but I'm maybe a little more confident than you are that we are trying to do the right thing here. Certainly, most of the programs I'm involved with, whether it's Energy Star or the Building America program that the Department of Energy runs, certainly we're very concerned about homes that are comfortable and healthy and safe and durable and all those things that are ventilation related, and they're all part of that program. And you're right, if you look at, say, an individual energy company's whatever things they're funding, let's say insulation of walls or something, where there is no health component of that. And at the individual component level, what you're saying is true. But I think there's much more awareness now of you can't just do one thing in a home without thinking about the whole house. And that means you've got to include the health and comfort aspects, and that means you've got to include ventilation. And that's why you see it in the Energy Star program. And that's why you see it in more and more utility programs. And that's why you see it even in building codes and so on. They're starting to require that you have to build tight, ventilate right. That I'm sure some of your listeners have heard that phrase before. That's where we're going, and I think that's a good thing.
Mm. As far as the programs go, and that's I would say the main marketing outlet for most of our industry at this point is the utility companies are mandated to give money to this kind of thing. They have a thing called the TRC, the Total Resource Cost. Here is my request for Lawrence Berkeley National Laboratory. Can you start to quantify the health and durability and safety benefits of the kind of control that you're wanting to exert over a building so that it's not just about the dollars saved on electricity and gas?
The short answer is yes, we can do that. The longer answer is how do we get there? Well, work that we're doing right now at Lawrence Berkeley National Lab is looking at all the different pollutants that you might find in a home, figuring out which are the ones that are common, which are the ones that are commonly at a concentration that might actually be a health issue, and then using health data that we have, this is not from LBL, that there's a bunch of people in the health world who've done this thing independently of our work, but we get to talk to them, play with them, use their information, and try and figure out, so what are the health impacts of these various things? And then we can convert that into something called the Disability Adjusted Life Year, or DALY for short. And this is a way that we put all the various health impacts together into one number that we can then convert into what is the health impact on you, and from that we can say what is the dollar value of that using various tables like they do for life insurance and so on that say, if you break a leg, what's the dollar value of that and your wasted future life and so on. And so that's how we can monetize those things. Although I will say that the difficulty there is healthcare is very expensive. So that makes the dollar numbers look very, very large for these health things, as you might imagine. And that means that often the health numbers will dwarf the energy issue quite quickly. It's a bit like the studies that some of you may be familiar with, where they've looked at productivity in the work environment. And a little bit extra air to make the space comfortable and to make the air nice to breathe costs you just a few dollars, but the productivity increase, because people are so valuable, completely overwhelms that. But unfortunately, that's a very hard story to tell, and it also makes people go, that doesn't quite sound right to me. How can that be so big? So it's not, we are sort of at the first stages of this, and it's not a concept that people are familiar with or used to yet. But I think that's the way we're going to try and monetize this whole issue. Personally, I think that we should also think about the non-monetary aspects of things, and this is very difficult in the utility environment that you described. Like, maybe it's just a good idea to have a healthy, durable home. Maybe that's good in and of itself, but that's hard to sell to accountants at the utility, right? And I don't want to bash on the utilities because they have to do what the various public utility commissions, if you have such a thing, are telling them to do, and there's always a bit of give and take going on there. So I don't want to point fingers at the utility programs. They usually have genuine people trying to do a good thing, and they will also sometimes say, they feel trapped by the total resource cost approach or whatever dollar valuing thing it is they have to do. But it's a very, very hard thing to break out of for any industry.
When we talk about return on investment, which is one of my least favorite topics in our industry, is it possible to use the approach that you just described where you get with the health care community and get that data together and come up with that number that you were describing and have health insurance providers and home insurance providers actually incentivizing home performance?
Maybe one day. I think that would be great. But frankly, I think we're a long way from that because there is a big disconnect between the healthcare community and the buildings community. They don't talk to each other very much. Their worlds do meet in things like hospitals, though. And if you look at how hospitals are ventilated, for example, they're ventilated very different than other spaces. There's a lot of ventilation going on because they have to really make sure that microbes and things like that are not getting transported around the building and are not being breathed in by the people in the room. So in a sense, in that particular environment, those two communities have come together and worked together and they find solutions. But the problem is ventilating a hospital is an expensive business. And life is full of compromises. I think frankly, it's not practical to ventilate your home the way you would ventilate a hospital, and you wouldn't want to. It's definitely overkill. So this is a situation where there isn't a right answer, right? You were always on a sliding scale of how much ventilation is enough. There isn't a number, right? There isn't one number that is the right answer. It depends on so many things, and certainly a hospital is one extreme. Right, and we're not going to ventilate our homes that way.
Yeah.
But certainly, I think that there is more sort of a coming together of these communities as time goes on. So it might happen in the future, but I think we're far, far away from your original point. I really think that's in the distance.
No, that's okay, but that was the most brilliant segue into my next question.
Just let me say, I think we're doing the best we can with what we know.
Awesome.
Which is what we should always strive for, right?
So what you just said, and I quote, there is not, some people need more ventilation, some people need less ventilation. It's not a number.
Right.
ASHRAE 62.2, 2013. First of all, you mentioned that engineers, who is most of the ASHRAE community who is going to use the standard, like tables. They don't actually want to have to do the calculation themselves, which is, getting to your point of, let's just make it plug and play. However, the number is pretty specific at this point, and there are a bunch of rules entailed with it. Can you just give us a behind-the-scenes look at how that... Well, first of all, what's different about ASHRAE 62.2 2013, which is a ventilation standard for residential buildings, from previous versions, and why it got there?
The why it got there is because homes have got holes in, and when the wind blows, or it's hotter or colder outside than inside, this makes airflow in and out of your house. If you open a window, air flows in and out of the house. So when we look at the ASHRAE 62.2 standard, it's really talking about how you mechanically ventilate a home. That is, you're using a fan to blow air in and out of the house. But we know that airflow through a fan interacts with all these other airflows that depend on whether or not it's a windy day or a cold day or what have you. And the reason for the main big change between 2010 and 2013 was that we used to assume that all that leakiness in the house, combined with the weather, gave you a number for how much airflow. And we gave you what was called the default infiltration credit, which was 2 CFM for every 100 square feet of floor area. And when you looked at the equation of the tables, that number had been assumed. You said, well, you've got that from the natural infiltration in the house, so now we're going to talk about fan sizing in addition to that airflow that you already have. But that was okay, but the problem is that the houses are changing, they're getting tighter in general, and people started asking questions about, is that default the right number? Why is it only one number? Because it limited how if you did a blower door test on a house to find out how leaky it was, we had a procedure for accounting for that to reduce the amount of airflow you had to put in with the fans also. But it made that very kludgy, because you had to say, well, it's the difference between that and the default, but you only get half the credit. And it quickly became complicated, and people were like, why only half the credit? Why this default? And it was not clear what was going on. So in 2013, what we did is we said, we're going to get away from that default. We're just going to say, what's the total target airflow? And so that default essentially got put into the target airflow. So if you look at just the equations and the tables, comparing the two standards, you see the 2013 one has got higher numbers in it because it's the total requirement. But we made what's the credit you get when you do a blower door test much simpler. You simply subtract it. There's none of this difference between the default and taking half that credit. You simply subtract it from that number. So it's much cleaner approach to dealing with this issue of how you combine what you get from the fans, the standard recommends that you install, and what you get from what's happening with the holes in the house. So it really was a big simplification. Mm-hmm. And it made it much clearer what was going on for people in the industry, I think.
I want to get back to that, but you mentioned the blower door, and the test that is prescribed in the standard is both a depressurization test and a pressurization test, which is not the way even people who are doing multi-point tests using a computer are doing it right now. How did they decide to make it that way so that it's kind of forcing people to do an extra step on the diagnostic side?
How was that decision made? I would say that's a historical issue. A long time ago, when we were first doing blower door testing, we realized that when we pressurize and depressurize, you would often get different numbers. And this is because a lot of the holes in your house, they don't let the airflow in the same direction, whether it's going in or going out. You can look at simple things like how windows and doors seal, but also all the little cracks in the envelope. Particularly if you have any house wrap or vapor barrier, that forms like a little valve. And so we realized these differences. And so we said, well, we better do it in both directions. We better pressurize and depressurize, because when the house is under natural infiltration, you've got air going in and going out. So you needed to, and the old test methods, we say you did both and average them, and that's sort of a reasonable approach to what you do to the house. You're right to say, though, that very few people do pressurization and depressurization. It's very rare. It's usually single point testing, 50 pascals, usually depressurization. And you're right that that's not what 62.2 currently says. And if you were to be totally hardline about it, he would say that these people are violating the standard of non-compliance. And I think that's maybe too harsh an assessment. The important thing is to actually do the testing. And the fact that there are ways to convert from that single point test to the information you need in 62.2 from the multi-point test to get a reasonable answer. And I think that people doing single point tests are doing a very reasonable job. It's an order of magnitude better than not testing. So me personally, I'm not speaking as the standard now. Me personally, I'm fine with single point testing and converting that number. It's certainly better to do pressurization and depressurization, but I can understand why people don't. So I'm a little squishy on that. I think it's fine that people are testing using a little simpler method, and it's possible in the future that the 62.2 test method will say it's okay to do that, and we'll have a little calculation in there that says how do you convert from one result to the other. But right now, you're right. You're in theory supposed to do it both ways.
There's so many questions. I love having you here. So my next question is the fact that what you just recommended, just doing a depressurization test or a one-point test, good enough for the business of installing a ventilation system, because the blower door test is not, in fact, the best way to measure actual infiltration and exfiltration through a house?
Well, the blower door test, you're right, it isn't telling you how much air is flowing into my house. It's telling you how leaky the house is. And to convert between those two, you have to know something about where the holes are in the house and what the weather is. And internally, in the ASHRAE standard, we've done lots of calculations to look at if you vary where the holes are in a house, and we looked at over 1,000 different weather stations in the US, and there's actually a table in the standard for all the different weather stations. So you just sort of look up your local weather station. There's a little weather factor in there that's actually used in the standard. So we do account for that weather variability within the standard when calculating the infiltration credit. And in fact, you're right. There is a step between measuring how leaky the house is and what the airflows will be. So that a house, say in Florida, in very mild conditions, if you take that same house with the same holes in it and stick it in Chicago on a cold winter day, of course the airflows are very different in and out of that house. And the standard accounts for that with its weather correction factor. And that's sort of been standard practice in our industry. And if you look historically at where houses were loose and tight, this was reflected by the fact that in northern states, and I lived in Canada for many years, and saw Canada in there too. And if you go over to Europe, the Nordic states did this too. They built tight houses, and they started doing it a long time ago because it's really cold, right? You don't want that cold air coming in. Whereas in the southern states, not so much, right? So that idea of the weather variability and how it drives airflows in and out of homes has been known for a long time. So effectively, we're institutionalizing this, if you will, by standardizing calculation procedures and so on. But this is really nothing new. We've known it's been around for a long time. This idea that yes, it's not just the leakage that matters; it's the weather that matters too.
Is the ventilation standard for existing homes as well?
Yes. And in fact, it has some special provisions in there because it realizes that sometimes it's easier to do stuff in new construction than it is in an existing home. And a classic example of that is for new homes, it's required that you have some sort of exhaust system in a kitchen and in a bathroom, because those are two rooms where we think there's lots of things generated in the house, whether it's water vapor, or it's odors from cooking, or odors from the bathroom, or particles that are coming off your cooking process. All sorts of stuff going on in those rooms. We decided you should ventilate those, and we call that source ventilation. You're ventilating where the pollutants are generated, when the concentrations are highest, which is the best way to do it. External exhaust fan, blow those outside. Seems like common sense. Great. But then you go to an existing home that doesn't have that. And it turns out that if you're in, say, a weatherization program and you have limited dollars to spend on every house, and you want to invest those dollars as much as you can in saving energy, because that is the focus of it, but at the same time you want to comply with 62.2. This is a question you asked at the beginning of our conversation about, shouldn't we do both these things? Shouldn't we ventilate, right? And they want to do that in weatherization, but their funds limited. It turns out that installing additional exhaust fans in kitchens and bathrooms can be quite expensive. You're cutting holes in the envelope of the building. You're cutting holes in the roof if you put the duct up to the roof. You're installing ducting, which means you have to pull out sheetrock, and then you have to get an electrician to come to run extra wires and pull extra wires. That can be an expensive business to install that fan. And so what the standard allows you to do, it allows you to have a higher, what we call whole house ventilation rate. This is a ventilation rate that's separate from the exhaust in those two rooms. It allows you to have more of that if you can't have an exhaust fan in one of those two rooms for various reasons. But you can only do that for existing buildings. That's not allowed for new construction. And so this was an idea brought to us by folks in the weatherization community who said, hey, we've got this issue. And we talked about it for a while within the standard. We came up with some new language that lets you do these things. And now the weatherization people are way happier with using the standard because it gives them this little bit of flexibility. If they're in a situation where it would be really expensive for them to do the exhaust in those rooms, they have a way where they can account for it with the whole house ventilation. And I think we have a better standard for that. And 62.2, although it's been around for a while, it's still an ongoing learning process. The more it's used, the more issues like this are coming up. Like the weatherization community decided this was really painful for us. Can you help us out? And the answer is going to be yes. And I think over the next few years, we'll probably see more of this as this standard becomes used more and more. And not just the use of the standard, but more ventilation being put in homes in general as it's required more and more. We're going to learn that, there's an issue when we do X or we do Y, and the standard needs to have some flexibility to deal with those things, and it will. Like all standards, it's officially written in stone and thou shalt do this, but about every 3 years there's a new version, right? And ASHRAE, who are the organization who oversees this standard, they have this standard under a process called continuous maintenance, where any time you can make suggestions on possible changes to the standard to the committee. And if you go to the ASHRAE website, you'll find the place where you can do that. And the committee will consider all of these suggestions. In other words, if you have something that you think would be a valuable input because you're encountering a problem or there's an issue, or you should definitely contact the committee, and the committee will listen to you. And you can attend our meetings and everything. They're open meetings. They're not behind closed doors or anything. And so the standard is very open to making changes. But we require that there's a really good technical, sound way of doing it. We're not going to do it arbitrarily. And you have to convince a group of about 20 people who are pretty smart. They've been doing this for a while, that your idea is a good one. But the process is there to make those changes, I guess, is my main point.
Bringing it back to the app.
Yeah.
If I have an app in my pocket that I can use to install a ventilation system, why can't we, in a couple of years, have the ventilation system run on an app that monitors the house and gives the house whatever it needs?
The problem there is that giving the house whatever it needs is the key bit. We simply don't have the ability to sense all the possible pollutants in a home in real time and have it talk to the ventilation system and ramp the ventilation system up and down. In commercial buildings, there are some controls that measure carbon dioxide, for example, and that's a surrogate for how many people are in the space. The idea being lots of people in space, they're doing lots of breathing, lots of CO2, and so they can modulate the airflow in commercial buildings. In homes, though, we don't have the same occupant density. There's not as many people in homes, pretty empty, and that makes CO2 sensing a very, very difficult thing to do because there's not enough of it getting generated to reach a point where you could, say, use it as a control thing. So those sort of standard occupancy things don't really work in a house. The other thing is we don't really have ways of sensing, say, particles, which are very, very important for health, in an inexpensive, robust, cheap way, because the inexpensive, robust, cheap is always the qualifier in all these things. You want to install something in a house, and it's got to work for 25 years, and it's got to be right, because you're saying, I'm going to ventilate properly based on what these sensors are telling me. And for sure, we have lab-grade equipment that will measure particle concentrations, but they have to be recalibrated all the time. And do you want one of these things in your home where you become the equipment recalibrator? Nobody wants that, right? And then you can think about all the various things that we come under the umbrella of what we call VOCs, the various volatile organic compounds. They include things like formaldehyde, which some of you may have heard of, but then there's a whole soup of these, hundreds and hundreds of different chemicals, and we just don't have a way to sense all those chemicals. Those technologies do not exist. Now, at the laboratory or research level, we can do a good job on some of them, some of the time, but again, not in a practical way you could put in your home and rely on this as a way to ventilate. And frankly, maybe we never will want to do that. You can imagine down the road, maybe sensors get cheaper, maybe they get better. But at the end of the day, there's always this nagging question about, well, what if one of those sensors goes wrong sometime in the next 25 years? How do you know? Because people don't sense a lot of these things, right? Odor, you can sense, but even that, your nose gets used to it, right? You get used to your own smell, that's for sure, right?
I've seen that many times.
So in the history of ventilation, all the original ventilation rates were set for odor control. And really, odor control is about smelling other people, not smelling you, because you get used to your own smell, right? So it's about smelling other people, and that's the origin.
So for a bachelor, we should install slightly more.
No, not at all. Surely the opposite. If you're at home alone and you're only smelling yourself and you don't care, you could get away with less, right? But it's your stinky roommates that are the problem, or your stinky dog, or the fact that somebody else is cooking in the house and you don't want to smell what they're cooking, whatever it is. So odor control is actually where a lot of this ventilation stuff started out.
And is there a way?
But just to get back to your question about will we ever sense all the pollutants in a home in a meaningful way to control ventilation, the answer is no, and we probably don't need to. That seems like a phenomenally complex thing to put in my house, and because there's a lot of uncertainty in things like how sensitive individuals are to a given pollutant. There's a lot of uncertainty about who's in this house. We don't know, right? And a ventilation system has to work for all the possible occupants the house could ever have. That, in this case, simpler actually is better. So long as we pick a way that is simple, covers most of the people most of the time for most of the pollutants, that, I think, is actually the best path, rather than trying to tailor all the individual emitting pollutants to your individual response that we frankly don't know. And probably that is even harder, knowing an individual's response. Oh, and all the responses of all the other people in the home. That's, this is the sort of the engineer's first take is, okay, I could answer that question, but I need to know huge quantities of information in real time, all the time, that we realistically won't ever know. So I think keeping it simple is the way to go. And keeping it simple means that it's robust. In other words, it'll still be ventilating 20 or 25 years from now when a totally different group of people in the house, and they've brought a whole bunch of different furniture in that's emitting at a different rate than your furniture, and they cook more often than you do, so they've completely changed the emission pattern. It's still going to work for them too. And so I think that's why we want to keep things simple.
Awesome. What is on the horizon that you're excited about in the next couple of years, research-wise?
Well, let's stick with ventilation, at least for a couple of minutes. One thing I think we're going to see is we're going to change what we do in our kitchens. Probably most of your listeners have a range hood, and I'm going to encourage them to use it every time you cook, because our recent work has shown that the pollutants that you get from cooking have a key one is the particles that are generated. And from a health perspective, we're talking about health now, not odor or comfort, but from a health perspective, that turns out to be the number one thing you want to watch out for in your home is the small particles. And cooking is the major source of them. And also cooking generates lots of water vapor, which can turn into condensation if you're not careful. And if you're frying fish, maybe everybody else in the house doesn't want to smell that, right? So there's an odor issue. You want to vent those things to outside. But our studies have shown, and if we just ask our friends and family and ask ourselves, frankly, how often do you turn on the range hood? Is it every time you cook?
Every time you burn something.
Right. That's right. If you're burning toast, true. But the rest of the time, no. We need to get into a world where a range hood turns on automatically and it vents to outside. Because the other thing that we see with range hoods is often they don't vent to outside. They just recirculate the air back into the kitchen. We call those forehead greases for the obvious reason. They blow greasy air in your foot. But we can't do that anymore. We've got to get those pollutants to outside. That's the major thing we can do in terms of a health impact is vent cooking properly. And I think a big change we're going to see is that we're going to have much better designed range hoods. We're learning a lot about what makes a range hood a good design. And they're going to become automatic so that every time you turn on the burner or you turn on the oven, it tells the range hood, hey, turn on now. This can be done really inexpensively, even as we speak. And we're working with manufacturers to do that. We're working on a test method to look at better capture efficiency so that we can do that kitchen exhaust by moving less air. Because right now, the only way you do it is you move more air. And those of you who've tried to do that know that's noisy. And one of the reasons people don't use their kitchen vents is because they're too noisy. We need to get to quiet systems. And we can do that with better design of the actual range hood itself. And we have done some experiments and talked to manufacturers. We can actually know the direction it has to go in. So I think that's a big major change in the ventilation world is much better kitchen ventilation.
By the way, listeners, if you want to hear more about that, there's an interview with Brett Singer on this show, one of the earlier episodes, and you should check that out as well.
Yeah, Brett is smart and great. He knows a lot more than me about kitchen ventilation.
He's a firecracker.
He's the researcher who's doing all the work. He's my colleague, and he's a great guy, smart, and they're doing the right thing there. So that's, in the ventilation world in homes, I think that's going to be something that you see. In terms of things like, is 62.2 going to make any major changes in the near future? I don't think so. But where it's going to be putting its focus for what changes it does make, I think, is looking at multifamily buildings. Right now, the standard definitely has a single-family focus. And what to do with multifamily is a question that comes up a lot because they are different. There's often things like architectural restrictions. I just spoke about venting kitchens directed outside. So that means that every kitchen has to have a hole cut in the wall and a duct put outside. Or there has to be a shaft incorporated in the building where you gang all these things together and put a single shaft with a fan on the roof. You're adding a lot of complication to multifamily, and we're just starting to deal with that. And the other thing with multifamily is something called compartmentalization, which is how much does each unit talk to each other unit in that space. And we talked earlier about leakage testing for homes. Well, when you try and do that in an apartment, when you do a blower door test, and you either blow air in or suck air out with your blower door, the airflow isn't just going through the outside wall. It's going through all the other walls and into the interstitial spaces in the apartment building. And this is very painful for folks like me who like to do energy calculations, because we want to know what's the airflow in and out through the outside wall. We do a blower door test, we get some number that is not that. It's everything. And so the standard currently talks a little bit, for example, about compartmentalization, but I think getting away from the standard for a bit, I think we're going to see much stricter requirements on new buildings for compartmentalization. And particularly in the transfer of things like tobacco smoke are a big, big red flag in the multifamily industry right now. People are getting sued because an occupant of one apartment is smelling the tobacco smoke of somebody else. And there are some municipalities and places who are saying, you just can't have that happen. And you have to build your new multifamily apartment building so that there isn't any transfer of tobacco smoke or other pollutants between apartments. And that's going to be a big issue, particularly as a recent trend, particularly in places like California where I live, is that we are building proportionally more multifamily now than we used to. Mostly for affordability reasons, but also for urban density reasons. There's all sorts of reasons to do it. And so this issue is going to get bigger. And I think this compartmentalization of multifamily buildings is it's a tough nut to crack, by the way. I'm not saying it's easy, particularly in a retrofit environment. If you've already built the building and you're trying to find all the holes that interconnect all the apartments, that's tough. And some, there are people looking into this. I do most of my work for the Building America program at DOE, and we have some of our Building America teams and other researchers are looking into this. And I think that's a nut we need to crack in the ventilation and air quality world, is what to do about apartment buildings. And of course that could apply to things like hotel rooms too. I think we could all agree we don't want to hear our neighbors or smell them in hotel rooms, right? Just like you don't want to in an apartment. Dorm rooms at a university. I mean, there's a lot of places where we stack our dwelling units together and we don't want them to talk to each other. And right now, they talk to each other a lot. And that creates all sorts of problems. So I think that's another big area where things are going to change in the world of ventilation. And the last topic, I think, for ventilation is I think we are going to get smarter. Having said a few minutes ago about how I like simple, I don't think we're not going to measure every VOC in a room. Not going to happen. But I think we can be smarter about our ventilation in a way that impacts our energy use. And you and I have been talking today about where energy and ventilation collide a little bit. And you can certainly imagine a very simple scenario of right now we tend to turn on a fan that runs all the time. What if instead of doing that, we didn't run the fan when it was either hotter or colder outside, depending on whether or not you're heating or cooling your home, but ran it more the rest of the time. So you got the same effective ventilation in terms of controlling the pollutants in the home. You just ventilate at different times. You would ventilate more when the system is on, and less or zero at times when the temperature difference, say, between inside and outside are bigger. So you move the ventilation around during the day to the times when it's going to cost you less of an energy penalty. That would be a really smart thing to do. And we have the technology to do it, and we developed a ventilation controller at LBL that we're in the process of doing some field testing of and working with some manufacturers might want to go into production. And the other thing you can do that our ventilation controller also does is you can sense the operation of other fans. So let's say you are cooking and you've turned on your range hood and you've got 100 CFM of airflow out through the range hood. But the whole house requirement was, say, only 50 or 60 CFM. Well, maybe then you can turn off your whole house fan now because of what's happening with the kitchen range hood. You can imagine a similar situation with a bathroom exhaust fan. Or for most people, the dryer, the clothes dryers inside the house. And that's a pretty good exhaust fan too. So if you knew those things were operating, you could then control or turn off your whole house fan. Now, the caveat here is, boy, you'd better be careful, right? You'd better make sure you're doing some calculations that make sure that you're not impacting the indoor air quality. And there's this principle called equivalent ventilation. I'm not going to go into any math with you right now. There are papers written on this. You can look them up. And the mathematics is a bit daunting, but we're not going to ever ask anybody to do the mathematics. That'll be hidden in the brain of a controller unit that will sense the operation of other fans. It'll say, I'm not going to ventilate in the winter between 4 a.m. and 8 a.m. And control the fans so that we minimize the energy impact. And we've done a bit of work on this, and the energy savings can be pretty significant, as you can imagine, if you can shift this time of ventilation and take advantage of other fans. You can save roughly 30 to 40% of the ventilation energy. So this isn't 30-40% of your energy bill, just a bit associated with ventilation. So if you want to convert that to what you would say on your energy bill, you got to divide by like 2 or 3 maybe. So maybe it's only a 10 or 15% of the total heating and cooling energy that you're saving using this method. But that's certainly worth saving. And when we're on the path to, if not zero energy homes, at least very, very low energy homes, that's an important aspect of saving energy, because we do want to keep ventilating. The answer to an energy efficient home is not to not ventilate, because you still want to have good indoor air quality. You want to have a healthy, durable home. And so this idea about a smart way of ventilating, because we can easily sense some things. We can't sense VOCs, but we know when a fan is on. I think there's a good future for that, and that's why we're continuing to research this. And we're working with some other folks right now looking at maybe we get smarter still and actually measure outside temperature, because plenty of modern heating and cooling systems do that already as part of their control strategies. Particularly anyone who lives in a dry, hot climate who has a residential economizer knows they measure outside temperature. So we could use that to make this even more sophisticated, possibly in the future. And there's a lot of other ideas about maybe we'll get clever about occupancy sensing that are coming down the pipeline. But I think smart ventilation is where we're going to go in order, particularly in high-performance homes, so that we can ventilate right while not having such a big energy impact. So awesome. Those are the 3 major things.
A lot more to talk about in future episodes. Hopefully you'll
be back. We could, I talk forever about these things.
Iain, thank you very much for being on the show.
Oh, it's been a pleasure. Thanks very much for coming.
Iain Walker is a building scientist with Lawrence Berkeley National Laboratory. You've been listening to the Building Performance Podcast from Green Dream Group in Chicago. I'm Corbett Lunsford. Tune in next time.